Today we are working on 4.4 Complex Zeros and the Fundamental Theorem, Day 1. When, when using real and complex values, the degree of a polynomial states the exact number of zeros, and each zero can also associate with a linear factor, even the complex zeros. The number of times a factor is listed is called its multiplicity. So if you see a factor listed 3 times, the multiplicity is 3. If you see a factor once, the multiplicity is 1. So let's look at how we deal with complex zeros. If we have x squared plus 4, we want to set that equal to 0 and solve. So if we subtract 4, we get x squared equals negative 4. We take the square root of both sides. We get x equals positive and negative square root of negative 4. The square root of negative 4 is 2i. So we get x equals positive and negative 2i. Now to create the zeros, we would take 2i. Because it's positive, we are going to have x minus 2i. For negative 2i, because it is negative, well, if we take x minus negative 2i, that would convert to x plus 2i. So as you can see, it kind of is the opposite of the initial 0. So we get x minus 2i, and we get x plus 2i. So just to be sure you understand, if I took x minus 2i and I were to solve that equal to 0, I would add 2i to both sides, and I would get x equals 2i. So to start with 2i, we subtract the 2i. We subtract our 0, which is why subtracting a negative would convert to positive. Okay? Here's an example. We have a polynomial that is given. We want to find all the zeros of p, real and complex. And we also want to factor p completely. Now this may seem a little bit backwards because usually you factor first to find the zeros, which we are going to do that. We do have a greatest common factor here. If I factor out x cubed, I will get x squared plus 9. But x squared plus 9 is a complex type of factor, which gives us the zeros, which then we can create the complex factors. With the x cubed, we set that equal to 0, and we get x equals 0. So we want to make sure anytime we have x, no matter what the exponent is out there, if it's just x, that is a 0 for our zeros of the polynomial. Now let's look at x squared plus 9. I'm going to set that equal to 0 just like I did above. I'm going to subtract 9 here, and I get x squared equals negative 9. I'm going to take the square root of both sides, and I get x equals positive and negative square root of negative 9, and the square root of negative 9 is 3i. So I get positive and negative 3i. So the zeros are 0, 3i, and negative 3i. Now that's my part A. For my part B, I'm going to take those zeros, and for the 0 value, I need to remember that that came from x cubed, so that's x cubed. For my 3i, okay, I'm going to take that and have x minus 3i, and for my negative 3i, that is going to be the opposite, so x plus 3i. So those are my factors, and I can write that out as x cubed times x minus 3i and x plus 3i. And those are my factors. Okay, well, let's look at another example doing the same thing. Okay, so again, we're going to have a polynomial given to us. We're going to find all zeros, real and complex, and we are going to factor p completely. When we look at this quadratic, or I'm sorry, not quadratic, but polynomial, we see that it is in quadratic form. So we know that because the middle term has an exponent that is half of the exponent from the first term. So because it's in quadratic form, we can factor this just like a quadratic. But instead of using x, we are going to use x squared. And if you have quad 3 on your graphing calculator, you can use that and remember to replace any x's with x squared. If I do the product sum rule for this problem, I have -2 and -1 for the product and the sum. And my two factors of -2 would be -2 times 1. Add those together, you get -1. So usually for a quadratic, I would write x minus 2 and x plus 1. But here, because it's x to the fourth, I need x squared minus 2 and x squared plus 1. So I'm going to set each one of these equal to 0. So x squared minus 2 equals 0. I add 2, and I get x squared equals 2. I'm going to square root both sides, and I get x equals positive and negative square root of 2. Now for x squared plus 1, I set that equal to 0, and I get x squared, need to subtract 1. So x squared equals -1. I take the square root of both sides, and I get x equals positive and negative square root of -1, which is positive and negative I. So these are my zeros. I have x equals positive and -2, and I have x equals positive and negative I. So those are my answers for part A. For part B, I'm going to take each one of those four zeros and make them into factors. So I take the square root of 2, and that is going to be x minus the square root of 2. I'm going to take the negative value of the square root of 2, and that is going to be x plus the square root of 2. Then you take the opposite. And for I get x minus I, and for negative I get x plus I. So writing those out, I'm going to get x minus the square root of 2, x plus the square root of 2, x minus I, and x plus I. And those are my factors of that polynomial. So we have A with the zeros and part B with the factors. Okay, let's look at this example here. And we need to factor the polynomial completely and find all its zeros, stating the multiplicity of each zero. And remember, the multiplicity is knowing if we have two factors listed and they are the same, the multiplicity of that factor or that zero is 2. If we have 3 of the same factors, then the multiplicity of that 0 is 3. So looking at this polynomial, it's a quadratic, but it is actually an unfactorable quadratic. If we take the factors of 17, the only factors we have are 1 and 17. They don't add up to -8, so therefore I cannot factor this. So what I need to do is use the quadratic formula or use quad 3 on my calculator if I have it. So here I'm going to take the opposite of -8 plus or minus the square root of -8 squared minus 4 times 1 times 17 all over 2 times 1. If I look at the radical, -8 squared is 64 minus 4 times 1 times 17. So we're still going to be subtracting, and 4 times 17 is 68. 64 minus 68 is negative 4. So now let's look at this. We get positive 8 plus or minus the square root of negative 4 over 2. Well, the square root of negative 4 is 2y, so we get 8 plus or minus 2i over 2. If we look at this, we have 8 over 2 and we have 2 over 2. And what we want to do is simplify both of those numbers. So we get 4 plus or minus I. So we can't do anything with the I. The I stays the same. It's almost like the coefficient of a variable. 2i over 2 is I. Okay? And 8 over 2 is 4. We cannot just do one of them. We have to do both. If we cannot do both of those to simplify, we don't simplify anything. So we have our zeros. Our zeros are 4 plus I. Whoops, I don't want that parenthesis there. So 4 plus I and 4 minus I. Those are the zeros. Now to create the factors, I'm going to do just like I did before. Okay, I take my 0 and I subtract it, right? So I take my 0, 4 plus I, and I'm going to take x minus 4 plus I. And because I'm subtracting a expression, it's a complex expression, but it's an expression, I'm going to get x minus 4 minus I. When I do 4 minus I, again, I'm going to subtract, so minus the 4 minus I, and I'm going to distribute, and I get x minus 4 plus I. So these are my two factors. So I would write that as x minus 4 minus I and x minus 4 plus I. And those are the factors. So nope, this didn't have a part A and part B. And that's all we have for day one.